On page 100 of our textbook, a page titled Visualizing the Atom, we attempt to summarize some of the main claims made in our current model of the atom. We can imagine a crystal, perhaps quartz, out of which we pull a single atom of oxygen. We have protons shown as pink circles with pluses and unlabeled gray spheres representing neutrons. And we see a green area throbbing around it representing the area occupied by the individual electrons. So this is a picture of an individual atom. As you can see, it's not a realistic picture. It's a kind of a cartoony picture. It doesn't actually show anything precisely. We can, as part of this model, describe the properties of the individual particles. We can say we have a nucleus and that the nucleus consists of protons with a property of a charge of 1 and a mass of 1. We can talk about a neutron, also found in the nucleus with a charge of 0, also with a mass of 1. We can talk about the cloud of electrons in constant motion outside the nucleus, and we can describe them as having a charge of -1 and a mass that's so small we can treat it as 0. We can summarize these claims about these subatomic particles in a table. Protons shown in red because they actually kind of glow a reddish pink color if you get them moving fast enough. The symbol P plus or plus, 1 atomic mass unit positively charged in the nucleus. The neutron N0, also 1 atomic mass unit but without a charge in the nucleus. The electron E minus, again with a mass so small it's negligible, we can treat it as 0. Its charge is negative. It's found in the cloud. And just as protons tend to glow a pink color, electrons tend to glow a green color if sufficiently excited. And so these are things that we treat as facts. These are part of our model of how the atom is structured, that it's made of these 3 main particles. And yet the interesting thing about this, this model has been accepted for a very long time, and yet no one has actually seen an individual proton, neutron, or electron. In fact, for most of the 20th century, it was impossible for anyone to say they'd actually seen an individual atom. They were too small to be visualized. Eventually, pictures were produced showing individual atoms using techniques that did not rely upon visible light, because as we're going to see, the waves of visible light are relatively large compared to an atom. You can't actually visualize individual atoms, even large atoms like gold, with visible light. You need waves that are smaller to detect them. Well, these subatomic particles are things that are much smaller than atoms themselves. They are 10 to 100,000 times smaller than an atom, and there is no technique whatsoever to visualize them right now, and there may never be. And so you are asked to believe that atoms, which are nearly impossible to see, are made of particles which are impossible to see, and you're asked to believe that this is true. Well, no one should accept claims like this without evidence. So let's just go back to square one. I mean, atoms, particles, too small to see. How do we know that any of this is true? It turns out that people have been very interested in the question of what matter is made of, and they were interested in it before there was science, before there was actually such a thing as the scientific method and the scientific enterprise. But there were smart people. And we often now call these smart people of the past philosophers, thinkers in the ancient world, who, in thinking about the evidence that was available to them, thinking about the ways different kinds of matter behaved, these philosophers were led to consider the possibility that all matter was made of invisible particles. One of these ancient Greek philosophers, Democritus, way back in the 4th century, claimed that there must be particles smaller than the human eye can see, the smallest things possible. And he called them atomos, which in Greek means uncuttable or indivisible. So small they couldn't possibly be cut anymore, the smallest things possible. It's interesting to realize that in the ancient world, in the Greek city-states and the Roman Empire that followed, it's interesting to realize that the really smart, educated people did not doubt that something like atoms existed. They had a beautiful indirect argument as to why they must exist. This argument was stated beautifully by the Roman politician and philosopher Lucretius. He provided many indirect arguments for those atoms in a famous poem called De Rerum Natura. In Latin, on the nature of things. Lucretius' argument goes like this. Videmus strata viarum saxi quibus plurimus, signa enia portus dextraque. Well, just kidding, I'm not going to read this. This is an ancient language. It has no living communities that speak it. It is Latin. I'm not going to read it to you in Latin, but I want you to understand that way back then, more than 2,000 years ago, there was a good argument. And let's hear it. Lucretius says, we see the cobblestones of the highway worn by the feet of many wayfarers. The bronze statues by the city gates show their right hands worn thin by the touch of travelers who have greeted them in passing. We see that all these are being diminished since they are worn away. Yet, but to perceive what particles drop off at any particular time is a power grudged to us by our ungenerous sense of sight. Well, that's very keen reasoning. Lucretius is saying, in effect, we see all over evidence that things are being worn away a bit by bit at a time, and yet we don't actually see anything fall off. There must be particles too small to see that escape our senses. It's very keen reasoning. And yet, what a pity that neither the Greeks nor the Romans nor hardly anyone else over the next 1,400 years bothered to do experiments to test these ideas. You see in the ancient world, clever people like Lucretius and Democritus, what they did was they came up with clever arguments based upon evidence, and then they just put them out there and they said, okay, my argument is clever, therefore it must be true. It did not occur to them to test their ideas by doing experiments, and it did not occur to hardly anyone else that followed. Modern science begins when we don't just take ideas that are clever and beautiful and say they must be true. Modern science begins when we subject even our most prized ideas to the test of nature, and we junk ideas that, well, don't pass the test. Now you might say, well, this is a terribly difficult thing. You're talking about atoms, and how could you possibly have an experiment that tested that idea? Well, it could be as simple as burning a candle. We did a lab where we burned a paraffin candle, and during the time we burned it on top of a balance, the candle's mass clearly decreased during the time that we were burning it. Yet at no time did I or you or anyone else involved in that experimental activity, at no time did any of us actually see any part of the candle leave. The candle must be made of a large number of particles too small to see. In other words, we actually tested the idea that atoms are real. Now, when we talk about models of the atom, we're not talking about a final ultimate truth. We're talking about a theory that happens to be extremely useful and very powerful. But our models of the atom are based upon evidence, and as evidence changes, our models have to change or they have to be rejected in favor of new models. That's the way science works. So we're now going to be talking about historical models of the atom, and there are many. And as we talk about them, I'm going to be giving evidence that led to their development, that led people to change previous models into the models we now have. In 1803, John Dalton, often called the father of chemistry, he imagined atoms to be like this. And this is not really terribly impressive. You know, it just looks like a tiny little red rubber ball. But he imagined an atom as being tiny and indestructible and having no internal structure. Now, you may not be impressed by this. It seems awful simple, again, just like a little red rubber ball, but able to use this model to do some marvelous things. One thing he's able to do is he's able to deduce that compounds exist, that there are substances that are made by combining elements. And he says they combine by definite whole number formulas like H2O. Evidence for this can be seen in experiments like the electrolysis of water. In the 19th century, people had discovered electricity and they started using it to investigate nature. Here we have a setup where a water is subjected to an electric field, and one side of the field is positive, the other side is negative. Here's a modern recreation of the same experiment, and you see that when we have that electrical field go off, we have bubbles of gas appearing in two separate test tubes, one on the negative side and one on the positive side. we paid careful attention. As we speed up the film, we can clearly see that more gas is being produced on the negative electrode than on the positive. In fact, about twice as much gas. The explanation is that something positively charged is appearing at the negative side and something negatively charged is appearing at the positive side. We're getting about twice as much of the gas at the negative electrode. And that gas is hydrogen, whereas the other gas is oxygen, occurring in a 2-to-1 ratio. And we can test that. We can tell these gases apart by the way they behave. Hydrogen will spontaneously combust. If we add a spark, a little miniature explosion happens. Whereas if we do the same thing with oxygen, no explosion, but instead a burning splint will burn more fiercely given the fuel. So these gases can be distinguished and they come in a 2-to-1 ratio. So Dalton deduced that water's formula was 2 hydrogens, 1 oxygen, and he came up with the notation H2O. Pretty cool. Now, how long did Dalton's model last? Well, not quite a century. Toward the end of the 19th century, J.J. Thomson at Cambridge University at the Cavendish Laboratory, he developed what's called the plum pudding model of the atom. In this model, we have an overall positive sphere. That is, the sphere has an overall positive charge, but embedded in that positively charged sphere are little packets of negative charge electrons, like in a plum pudding or like chocolate chips in a chocolate chip cookie. We have electrons that are negatively charged in a positive sphere. Now, why did Thomson find it necessary to add this notion of charge to the atom? Well, he had done some experiments. These experiments use what's called a cathode ray tube. It's a hollow tube which has mostly air pumped out of it. The inside of the tube is coated with a compound that will glow when it encounters charged particles. And the cathode ray tube is connected to a power supply. And when the supply is turned on and electric charges start streaming through the tube, we see something interesting. We see an eerie green glow. Now, people had developed these tubes and they were studying the green glow. And what Thomson was able to prove is that you could get this green glow not just by connecting it to batteries, but by connecting it to samples of actual matter. Here you see a video clip that shows one of these traditional cathode ray tubes being demonstrated. And what do you see? Well, you can actually observe that the green line, which represents a glow of charged particles, that line can be deformed, pushed toward or away by moving a magnet around a tube. So Thomson observed these particles coming off of ordinary matter, and so he concluded that there was a particle called the electron carrying this negative electric charge, and that it was part of an atom structure, and so we had to have a model that included electric charge. Well, how long did Thomson's model prevail? Well, not quite 10 years, maybe a little bit more. One of his students, a New Zealander named Ernest Rutherford, he graduated from Cambridge University and he went to a college in Canada. And he did an experiment there, and quite by accident, he discovered the proton. And as part of discovering the proton, he was forced to conclude that we needed a model that shows the electrons in constant motion, and that the proton and its mass could only be accounted for if we said it was located in the very center of the atom. And so he not only discovered the proton, he discovered the atomic nucleus. In the model that you see on the screen, where we see little, electrons going around the nucleus, kind of spinning like little orbits. This is actually the mental picture that many people still have of the atom. This is not the current model at all, as you will see, but this is a very popular model because it reminds people of a little solar system. Well, what caused Rutherford to imagine that we had to have a nucleus, and why do we have to have a proton, and so on and so forth? Well, it's due to an experiment. Rutherford was actually trying to figure out the size of gold atoms, and so he had set up a piece of gold foil, and he was shooting at the gold foil with particles called alpha particles. Radioactive materials have been discovered, and some materials have been shown to be producing these little particles that would shoot out like little bullets. And so he's using the little bullets as an experimental probe. he shoots the little bullets, the alpha particles, at the gold foil, and all around the gold foil there's a series of screens that are coated with the same material, same sort of material that you find inside a cathode ray tube. It's stuff that's sensitive to charge, and so as the particles would glance off the gold foil, they would hit the screens behind, and they would leave a little mark on the coated screens. And that part of the experiment was working really good, and Rutherford was planning on seeing how these things bounced, and by using some fancy math, he was going to figure out by the way the alpha particles bounced off the foil, he's going to figure out, you know, how big the gold foil atoms actually were. But something astonishing happened. Every now and then, instead of glancing off and hitting the screens at an angle behind, every now and then one of these particles would reflect straight back, as if it had collided with something that was very small but super dense. Rutherford was stunned by this result. He said it was like I shot a cannonball at a pillow and the cannonball bounced back. He could only explain this by concluding that there had to be something at the very center of the atom that was very small, that was very dense, and probably positively charged, the atomic nucleus. This is one of the most famous experiments in the history of science. Well, how long did Rutherford's model last? It didn't even last 10 years. A Danish student, graduate student, was visiting Cambridge, and he didn't actually do any experiments, but what he did was he looked at the data that was coming out of the work at the Cambridge laboratory by people like Thomson and his successors, and he observed that the energies being observed from the newly discovered electrons could best be explained by assuming that they were not only in motion, but they were moving in regular orbits that had a certain fixed distance from the nucleus. That is, they were a certain distance away, and the amount of energy associated with the electrons could be explained that by they were either gaining or losing energy when they changed their orbits. This model was not directly tested by experiment for some time, but it was very popular because it explained something that had been previously mysterious. Bohr's model explained the fact that when you got different elements excited, that is, when you took a sample of an element, you got it really hot, you got it really moving fast, you know, the element would tend to glow and it would produce particular colors, but not any possible color, only particular color. And this could be explained by the idea that the amount of energy that was either being gained or lost wasn't just any amount of energy, but that it came in packets of a certain size. They came in packets that were a whole number, a number that was related to the size of the hydrogen atom itself. The energy, instead of being continuously variable, was discretely variable. It was either 1 or 2, 2 or 3, 3 or 4. The energy was said to be quantized. This model was beautifully explained something that was already known, which was that if you took hydrogen atoms and you ran electricity through them and you looked at the light from a hydrogen atom, you didn't see all the colors of the rainbow. When you took that light from a hydrogen atom and you put it through a prism, it separated into specific colors, what we call spectral lines, individual wavelengths of light. And Bohr's model predicted the exact colors of light you would see. That's quite impressive. Eventually, people did this trick with all the elements, and they discovered that every element has a unique combination of colored lines produced in the same process. We call these lines atomic emission spectra because they're emitted by atoms and because they form a series of colors like the spectrum, like the rainbow. Only every element rather, has its own unique pattern of lines that fits that element like a fingerprint. Scientists can use these spectra to identify chemical elements in whatever light we're looking at. It could be the light of a distant star. It can be the light from a compound that we've ignited and which is fiercely burning in the atmosphere, such as fireworks. The compounds in fireworks have distinctive colors. Why is that? Well, because every element, when you get its electrons excited, emits particular wavelengths of light that, again, can be used to identify that element the way a fingerprint can be used to tie a criminal suspect to a crime scene. Here's how it's done. We take light from a source and we move it through a barrier that has a tiny little slit. The narrow beam of light is put through a prism, and the prism can separate the light waves into individual colors. If we do this for a regular light bulb, we will get all the colors of the rainbow. But if we use a special lamp that is filled only with the gas hydrogen, we'll get a different result. The light moves through the prism, but instead of a continuous spectrum of all the colors and visible wavelengths, we get only a few narrow bands of color. These few discrete lines, this pattern of wavelengths, is unique to the element, in this case, hydrogen. Now, if this all seems very strange to be talking suddenly about light in a chemistry classroom, well, you have my sympathy. But please understand that the light that we see with our eyes, that's only a tiny sliver of what's called the electromagnetic spectrum. Space is filled with radiation. Some of the radiation we can see, the colors of the rainbow, red, orange, yellow, green, blue, indigo, violet. We can see those colors because our eyes have sensors that are tuned to that narrow range. But there are waves that are larger than visible light, infrared, microwave, radar, and radio. They're there too, but our eyes aren't tuned to sense them. There are also waves that are much smaller than those of visible light, ultraviolet, X-rays, gamma rays, cosmic rays. But again, our eyes aren't tuned to see them. And yet they're all electromagnetic radiation. They are all light. And since they are light, they all have the same speed in a vacuum. Here we use the symbol lowercase c for that speed. Why c? Because the speed of light in a vacuum is a constant. Now, since this constant is true, that means that it's essentially the same speed throughout the universe. And this speed here shown is 2.997 E8. That speed is basically 300 million meters per second. 300 million meters per second. And this is true whether the wavelength is long or short. Here we use the symbol lambda, which looks like an upside down Y. We use lambda for how long the wave is, because it's the Greek letter for L, for the L sound. And it doesn't matter if your wave is long or short, big or small. What matters is that all these waves, regardless of their size, travel at the same speed in the vacuum of space. Shorter waves have a higher frequency than longer waves. Why? Because since they're shorter, you can fit more in the same space. We measure the frequency of waves in waves per second, or sometimes we say hertz. But if you have a big wavelength, you'll have a low frequency. Your waves will be longer. If you have a very short wavelength, the waves will be shorter. And so frequency is inversely proportional to the size of the wavelength. That is, if the wavelength is big, the frequency is low. And if the frequency is very high, the wavelength must be big. In any case, the speed of light, c, is a constant. And since it's a constant, that means the product of wavelength and frequency is also a constant. So if you take the speed of light and you divide it by the wavelength lambda, it will equal the frequency in hertz. But if you take the speed of light and you divide it by the frequency, it will equal the wavelength in meters. So it's a constant relationship. It's really kind of a beautiful, simple idea. So either the frequency or the wavelength of any color of light can be calculated in this way. And it doesn't matter whether that wave comes from a star or from a radio station here on Earth or from a glowing chemical compound. So you're going to use this understanding to help you do the calculations in the second part of the lab activity. And then at the very end, and this is elegantly simple, you can simply figure out the energy that's involved by multiplying the frequency of your calculated wavelength of light, your particular color. You can just take the frequency of that color of light and multiply it by a constant, Planck's constant, and that will tell you the amount of energy associated with that particular frequency of light.